Okay, so I'm hoping that at least by the end of today I'll write down an action for the string field theory. Okay, so let me begin. So there is some cutoff somewhere here, right? Okay, so yesterday we discussed the fact that while a general offshell amplitude was written as integral over SGMN of this form, okay, and I had defined what this form is. Okay. This we started by saying that it should be a section, but what I learned by the end of yesterday is that it need not be a section, it can have vertical segments, okay, and those are important in dealing with spurious poles. Okay, so these can have vertical segments. So today I'll generalize it even further, okay, and that seems to be what is necessary for the full formulation of string field theory. Okay. That these sections could also be generalized sections of the following form. This could be formal sum of sections where these are sections with vertical segments. And these wi's are some weight factors, some numbers, such that sum over iwi equal to 1. Okay. And this basically means that instead of taking integral over a single section, you could take integrals over different sections and average. Okay, so by definition, integral over SGMN is equal to sum over iwi integral over SIGMN. Okay, this is what you'll mean by having an integral over this generalized section. Okay. And so from now on, whenever I write a section, when I talk about a section, it will refer to a generalized section where each of the component sections could have vertical segments. It could be also uncountably infinite. I mean, we'll see that you will also need integrals. Yeah, typically always, I mean, at least it's necessary only for PCO directions, right? But you could presumably also do for the other directions, even though that doesn't seem to be any reason to consider such vertical segments. Okay, so now the goal today is to try to see if the offshell amplitudes that I defined yesterday, okay, could be identified as coming from a string field theory. Look for string field theory that gives these amplitudes. Okay. And we will see that in order for having an interpretation in terms of string field theory, we have to put further restriction on these sections. Okay, for arbitrary choice of these sections, you will not have interpretation as the amplitudes of string field theory.
I had a question about this particular expression yesterday.
Yes.
On this vertical segment.
Yes.
So, you had said that there are spurious poles
yes.
which come from two different kinds of origins.
Yeah.
One kind of origin was
when two picture changing operators collide, for example.
Operators colliding. And the others were just these, even when none of them collide.
Yeah.
Because from the beta gamma system, the motionized beta gamma system, there are additional
zero singularities. Yes.
So it is clear that the first kind of singularity probably could be avoided by jumping the picture changing operator. But is it obvious that the second kind of singularities are also avoided?
Yeah, because if you look at the dependence on where the singularities are, they depend on the locations of the picture changing operators. So by making the picture changing operator jump, you can shift the locations of where the poles are. Right?
So even this spurious singularity which come from Bose-Einstein beta gamma system.
Yeah, because picture
Chaining operators being in particular position.
exactly, that's right. Because the picture changing operators know about, those operators have non-zero picture number, right? Which basically means that they have non-zero charge under the Bose-Einstein beta gamma system, and that's why they actually affect the spurious poles. So if you change the location of the picture changing operator, you actually shift the position of the spurious pole, right?
But is there a physical understanding of where the picture changing operator should be, like when the spurious pole happen?
Yeah, there is a physical understanding, and basically the understanding is that if you put the picture changing operators in a certain way, and that means that now if you insert an extra beta or gamma in the correlation function, you are allowing certain zeros and poles. Okay. And what you find is that the spurious poles occur exactly in positions, okay, where the gamma develops an extra zero mode. Right? Once you allow those many zeros and poles in the gamma, it develops an extra zero mode, and because gamma is a bosonic field, right, the integral over that zero mode gives infinite result. Right? So that's the physical understanding of why these spurious poles appeared. But for what we are doing, right, all we need to know is that they occur on codimension 2 real codimension 2 subspaces, and that their position depends on the locations of the picture changing operators, so that by moving in the fiber direction, you can avoid those poles. Right? And that's what you are exploiting in these vertical segments. Okay, so you have to look for a string field theory that gives these amplitudes. Okay. More specifically, what we look for, see, once you have a string field theory, okay, then the amplitudes will be sum of Feynman diagrams. Okay. And what we'll aim for, okay, is that each Feynman diagram will give you part of this generalized section, okay, and the sum equal to the total SGMN. Okay, so in other words, the Feynman diagrams, okay, will each give part of the section. So if you have a section like this, okay, each Feynman diagram will give a piece of it. So this may come from one Feynman diagram, this may come from another Feynman diagram, and so on. And at the end, they have to all fit together to give this continuous subspace SGMN. This is the aim.
A general off-shell amplitude which, as you have defined, which may not come from a string field theory. Is there something bad about it?
Yeah, basically they will not satisfy factorization property. Right? I mean, I'll describe what condition you are going to impose, and that will make it clear what is the problem with the general off-shell amplitude. So they will not satisfy off-shell factorization.
So that's the...
Yeah, exactly. Okay, so to see what kind of constraints you need to impose, okay, let's consider some property of a Feynman diagram. Okay, so let's suppose that you have two Feynman diagrams. And I should add here that whenever I am talking about Feynman diagrams, okay, it will be understood that in the internal legs we are summing over all states. Okay, so we don't label the internal states, internal legs by some state. Okay, we allow all states to propagate. Okay, of course, some states may not propagate because of the conservation law of the vertex, but in general, we allow all states to propagate. Okay, so given two Feynman diagrams like this, okay, we can find a new Feynman diagram simply by joining two legs. Right? This is one operation that you know we are familiar with from Feynman diagram. And a very related operation is that if you have a Feynman diagram like this, we can join two legs of the same Feynman diagram to construct a new Feynman diagram. Okay, again, this is something we are quite familiar with, right? Just from Feynman rules. Now, what does this mean in terms of these? Okay, maybe I should, let's say, so these ones will refer to as a section segment. Okay, because this is really the segment of a section.
Why do you consider use these two operators? You could have joined many more legs in one.
Yes, but they are all combinations of these. Right? Yes, you can join many more legs, but you can do it step by step, right? You can first join this and then you joining this now is like this. So these are the basic operations that you want to understand. Okay. So the issue is then that these must represent some operation on the section segments. Okay. Let's suppose you are given the section segment of this one and the section segment of this one, then there must be an operation which gives you section segment of this combined Feynman diagram or section segment of this Feynman diagram. Okay. And the question is, what is this operation? And the string field theory, okay, at least the standard formulation of string field theory gives a very specific answer to this, which is called either swing or sometimes also plumbing fixture. Okay, so which is what I'll try to explain now. So let's consider this one. Okay. So this should correspond to a section segment, which means a collection of Riemann surfaces. Okay. This should also correspond to a collection of Riemann surfaces. And now this joining will give you another Riemann surface or another collection of Riemann surfaces with more genus, because if it has G1 loops and it has G2 loops, it should have total G1 plus G2 loops. Okay. And number of external legs also change. So this operation of swing is the following. Okay. So suppose the W1 and W2 are the local coordinates around the two punctures. See, punctures on the Riemann surface represent the external lines, right? That's where the external vertex operators are inserted. So this corresponds to some Riemann surface with a specific puncture, okay, where we are going to join by this leg. This corresponds to another Riemann surface with a specific puncture. So we assume that W1 is the local coordinate around this puncture, W2 is the local coordinate around this puncture. Okay. And then we show the two Riemann surfaces by simply making this identification. Okay. So geometrically, what it means is the following. Okay, take a Riemann surface like this with lot of punctures. One is spatial. Okay, this is the spatial one, which around which W1. So take another Riemann surface. Okay, again a spatial puncture. Okay. So we cut out a circle which is at mod W1 equal to e to the minus s by 2. Here you cut out a circle which is at mod W2 equal to e to the minus s by 2. Okay. And then we identify these two circles. Okay, that's what this means. Okay. So once you identify these two circles, you see you have got a big Riemann surface now, okay, which has genus. If this was as genus G1 and if this was as genus G2, okay, then the new Riemann surface will have genus. So see, we start with sigma G1 M1 N1 and sigma G2 M2 N2, and the new Riemann surface will have genus G1 plus G2. how many external legs, okay, you see that the number of external legs will reduce by 2 because these two will now be part of the sewing process, so these will not be external legs anymore, right? Just like the Feynman diagram over there, once you join these, you are losing 2 external legs from the 2 Feynman diagrams. Okay. So there are 2 possibilities. One is that these are Navier or NS states, okay, in which case you will get M1 plus M2 minus 2 and N1 plus N2, okay. Or we can have a Ramond swing which is G1 plus G2 M1 plus M2 N1 plus N2 minus 2. Yes, that's a standard plumbing fixture, okay, but we are allowing this S and theta to run over a specific region, 0 less than or equal to S less than infinity and 0 less than or equal to theta less than 2 pi. Now, this sewing process, okay, in fact, not only generates new Riemann surfaces, okay, this also generates local coordinates around each of these punctures, right? Because there are already local coordinates are defined around these punctures, so it just induces new local coordinates around these punctures, and similarly local coordinates around these punctures, okay? And it also induces picture changing operators on the combined Riemann surface, because these had picture changing operators, these had picture changing operators. So it gives you an arrangement of picture changing operators also on the combined Riemann surface. Okay. So in this sense, it really joins, it just doesn't show Riemann surfaces, it shows elements of P tilde GMN. Right? You take a point in P tilde GMN, which is a Riemann surface equipped with local coordinates and picture changing operator locations. You take another point in, say, P tilde G1, G2, M2, N2. And it produces a new point in P tilde G1 plus G2, either M1 plus M2 minus 2, N1 plus N2, or this one. So the claim is that it takes section segments two section segments and gives you one is P tilde G1 M1 N1 and P tilde G2 M2 N2 and gives a section segment of P tilde G1 plus G2 . But for this, let's count the dimensions. Because a section segment is not just a collection of points in P tilde GMN, it also comes with a very specific dimension, right, which is 6G minus 6 plus 2M plus 2N. Okay. So if you get a subspace which is either less dimensional or higher dimensional, then you cannot call it a new section segment. Okay. So what is the dimension of the section segment? So the original section segment of this one, okay, had 6G1 minus 6 plus 2M1 plus 2N1. This was the dimension of the section segment of this. The one of this is 6G1 minus 6 plus 2M2 plus 2N2. 6G2, thank you. Now let's see about this. This is 6G1 plus G2 minus 6 plus 2 m1 plus m2 minus 2 plus 2 n1 plus n2. Okay, and for this, it is 6 g1 plus g2 minus 6 Now you can compare the left and right hand side and you find that they don't really match. Okay, this is, you just count the constants, this is minus 12, okay, whereas this is minus say 10, this is also minus 10. Okay. And this is precisely the reason, okay, why you have to introduce this two parameter family of surfaces, S and theta, right. So if you add 2, okay, from S and theta, okay, then you see that indeed the dimension here matches the dimension here. Okay, if you add one more parameter, okay, then it will have two larger dimension to be interpreted as a section segment. Okay, but with just two parameters S and theta, you precisely get a section segment of the new Riemann surface. Okay, I'll not do this. This is more or less the same. Okay, it's just the 2 points on the same Riemann surface. Okay, so let's just focus on this. But there is still a subtlety. Question? Yes.
So when you sew these two functions together,
Yes.
What was before a disk
Yes.
becomes a part of the sphere regions that you had defined.
What was a disk? Meaning it's like if you take two 3-punctured spheres, right, and sew them like this, then it becomes a 4-punctured sphere, right? You cut out a small hole from the first sphere, small hole from the second sphere, and join them together.
Okay, but yesterday the way we had put the disks, we had the disks and the 3 punctures.
Oh, okay. So those disks were, yes, around the punctures, yes. So you remove those 2 disks from around 2 punctures and then join them together. Exactly.
And you join them. So do you convert them into another 3-puncture sphere?
No, you don't have to. Okay, so you are asking that now if you want to reinterpret them, right? Yes, so there you think of that where you are joining as another circle, where you have to give the overlap condition, right? Then both sides become 3-punctured spheres again. Okay, let me try to remember what we did. So let's look at locally what we had, right? We had something like this, right? We had this, there is a puncture, here you had a disk, right? So once you remove this, right, this is already a 3-punctured sphere on this side, and on this side you like have a 3-punctured sphere. So as long as you include this circle as the one on which you are doing the overlap, right, you have still 3-punctured spheres put together. No, we still have spheres with 3 holes. See, if you don't have this circle, okay, let me draw this. So you remove this circle, right? There is a similar circle. So now on this side, so you have something like this. We had this, right? So here, both sides had a puncture. You just remove it, right? And you think of this as a new hole, right? So now you have this a 3-punctured sphere. This is a 3-punctured sphere, right? And this is, you have to specify the overlap function on this. Okay, so that's the one way to interpret this. But I should again say that this picture that I drew yesterday, that is artificial, that you could use other pictures also, right? It's just one way of labeling the coordinates on P tilde GMN, okay? But that's certainly not the only way. Okay, so let's look at the picture changing operator counting. So picture changing operator counting, how many were there on this side? Okay, and you have to do this counting for separately for NS and R. Again, on the left hand side there is no confusion. 6G1 minus 6 plus M1 plus N1 by 2. Right? This is the total number of picture changing operators that you had on the left. Okay. Then we have 6G2 minus 6 plus M2 plus n2 by 2. This is on the right. Okay. How many do we need? Okay, there are two different cases you have to consider. So for this case, not 6g1 minus 6, 2g1 minus 2, sorry. That was 6g1 minus 6 was for the dimension counting. Okay. And similarly, this is 2g2 minus 2. For this, we need 2 g1 plus g2 minus 2 plus m1 plus m2 minus 2 by 2 plus m1 plus m2 minus 2 plus n1 plus n2 by 2. And for this one, I need 2 g1 plus g2 minus 2 plus m1 plus m2 plus n1 plus n2 minus 2 by 2. Okay, I'm just using, so these many were induced from the original Riemann surfaces. Okay. This is what I need if the swing is done at a NS puncture. This is what we need if it is done at the Raman puncture. Is this counting okay? Now you can easily verify that this is fine. Okay, you have a minus 2, that's minus 4. Here you have minus 2, that's minus 4. Okay, so the two numbers agree. Okay. But for this, there is a problem because here you have minus 4, okay, whereas the number that we need is minus 2, minus 1, that's minus 3. Okay, so which means that for when you are showing Raman puncture, okay, what the situation that you have is that the number of picture changing operator that is induced from the original two Riemann surfaces is one less than the number you need. Okay. So you have to explicitly specify where to put that extra picture changing operator. Okay, we are missing one picture changing operator. So the consistent prescription is that you insert the picture changing operator not at a single point but as averages, okay, and that's where these generalized sections come into play, which I had written down there. Okay. You insert this is around this circle. Again, I have erased that picture. The circle along which you glue, right here. Okay, this one or this one. And by the relationship between W1 and W2, you can easily check that this is also the same as dW2 over W2, I of W2. Okay, this is a dimension 0 primary, so these two are just equal, and dW1 over W1 is the same as dW2 over W2 up to a sign, but that sign gets compensated because the contour of integration is also reversed between W1 and W2. So this means that you have to use generalized section. Because we are averaging. We are not inserting the picture changing operator at a given point, we are actually making an average over a continuous set of insertions. Is this okay? Are there questions? Yeah, this is like the zero mode of the picture changing operator. The picture changing operator is a dimension 0 primary, right? And this is the zero mode of the picture changing operator, but zero mode of this composite operator. Yeah, it's not clear if this is a unique choice. It has to satisfy various consistency conditions, right? In particular, whatever operator you insert must commute with this B0 minus and L0 minus, right? And in some sense, it should be symmetric between the two sides, right? And this operator has all these properties, right? I mean, if somebody can cook up some other operator with these properties, then that may be equally good. right? The point is, I think if one finds another operator which is also equally good, what this probably means is that the corresponding string field theories that we will get will be related by field redefinition. Okay? That seems to be the general lesson, that string field theory that we will be constructing, right, has a lot of freedom, but that freedom you can show is just a field redefinition of fields, that you can take, if you take different class of sections satisfying this showing condition, right, you get different looking string field theories, but they are all related by field redefinition, and that's likely to happen if there are other choices here. Okay, but at least this is one choice we know that works. But I mean, the requirement that this commutes with these two, yeah, that's a strong constraint. Right? And this, for example, requires that you have to integrate. Right? If you insert it at a given point, it's not going to be invariant under L0 minus rotation. Okay, are there other questions? Okay, the other point I wanted to mention here, okay, is the S goes to infinity limit. And you can see from this picture what happens in the S goes to infinity limit. Okay. So imagine that these two Riemann surfaces has been sewed to each other, right? Mod W1 equal to e to the minus s by 2, identify mod W equal to e to the minus s by 2. Okay. And you can see that in the S goes to infinity limit, these two circles shrink to 0 size. Right? That means that you are taking gluing two spheres, okay, with an infinitely narrow neck. Right? And that's exactly what we called degenerate Riemann surfaces. Right? So S goes to infinity limit in this language is a degeneration where the glued Riemann surface actually splits apart into two other Riemann surfaces. Right? That's the source of the infrared divergences, as we discussed earlier. Okay? And we will see soon that this S that we have introduced here, okay, let's see here, this S will play the role of the Swinger parameter. Okay? And we had seen that in the language of quantum field theory, S goes to infinity is the infrared limit. Right? And this makes manifest the relationship between the infrared divergences, okay, which we had, we had motivated earlier. Okay? But from this picture, it will become absolutely obvious that the infrared divergences in the corresponding string field theory, which comes from the infinite Swinger parameter limit, is really the degeneration limit of the Riemann surfaces. Okay, is the same singularity that appears when the Riemann surface degenerates. Okay? And the connection comes from this showing relation. Okay, the large S corresponds to degenerate Riemann surface. Yes.
I'm still a little confused about the generalized section.
Yes.
Since you were introducing two additional moduli, the S and theta, in this plumbing fixture, it's not completely obvious to me that the averaging is over the fiber directions and not on the, that this W integral, you could trade off for a theta integral on the...
Yeah, then you have to put a theta integral on both sides. See, the point is that you could take, then you have to take true theta integrals. Because it's like you're showing two Riemann surfaces, okay, with a, and you are turning one with respect to the other. Right? If you insert a specific W at a specific point, right, then as you are rotating theta, right, that point also gets rotated. Okay. Whereas here what you are doing is that you are at a fixed theta, okay, and you are integrating over all possible W's. Then you change your theta and you again integrate over all possible W's. Okay. So in this sense, this integral has to be done at fixed theta. Okay, and then you do your theta integral.
And it's not enough to, you couldn't do it by, I guess you couldn't talk of averaging over theta.
Yeah, so that will correspond to, I mean, you could do that if you introduce two thetas, right, and a cylinder in between, and then if you independently integrate about both of these thetas, that would correspond to this kind of averaging. Okay, but because you have done in introduce only one theta, right, you still have to do this averaging explicitly. I mean, I think when we write down the propagator, it may also become clear exactly what this corresponds to.
Counting PCOs work the same even for the non-split.
Yes, I mean you can do a similar counting there.
So there also, when you see the Riemann functions,
You have to introduce this, yes. So that part I will not do explicitly.
And just one last.
Yes.
Is it only for Ramond sector states that you need to use generalized sections? If you add correlators?
Yeah, meaning you could do this also for the NS sector, right? In fact, for some cases you can show that you need these generalized sections also for NS sector, just because you want to make sure that the amplitude is symmetric in the external legs. Right? So suppose you have 3 NS sector vertex operators on the 3 puncture sphere. Okay? On a 3 puncture sphere, you have 3 NS sector vertex operators, and you have to insert a PCO somewhere. Right? And what you can show is that it is impossible to find a PCO which is symmetric in all 3 punctures. Right? This is one of the properties of a Feynman amplitude, Feynman diagram, right? It should be symmetric in all 3 punctures. That if you exchange so in other words, if you suppose you have put the punctures at 0, 1 and infinity on the sphere. Right? Now you make an SL2C transformation that exchanges 0 and 1 or 0 and infinity or 1 and infinity. Right? And you have to make sure that the PCO is inserted at a point which is invariant under the SL2C transformation. Right? And that turns out to be impossible. You cannot find a single location, right, which is invariant under arbitrary SL2C transformation that exchanges all these punctures. Right? But if you take the average between 2 insertions, right, then it becomes symmetric. Right? So in that sense, even for the NS punctures, this is needed because you need the vortex to be you want the vortex to be symmetric. Okay, so what this picture tells, so what has, okay, let me again recapitulate what we have done. So what we have done is to give a procedure, okay, by which if you know the section segment of 2 Feynman diagrams, okay, you can find the section segment of the combined Feynman diagram. Okay, you have no freedom in getting the section segment of the combined Feynman diagram because that's already induced by this procedure, right? The PCO insertions are all fixed, the local coordinate choices are all fixed, so you have no freedom. Okay, you are automatically led to the section segment of the combined Feynman diagram. Okay. So this means that if somebody gives you the section segment of just the elementary vortices, okay, a Feynman diagram where we have no internal propagator, okay, just the elementary vortex, okay, then from there you can build the section segment of all Feynman diagrams. Okay. So the only data that you have to give is the section segment of the elementary vortex. Okay, everything else is induced from there. Is this clear? So given section segment no, not just 3 puncture sphere, all elementary vortices. So we'll have elementary vortices of all kinds. No, there is no, at least in open string field theory you can do that, but in closed string field theory there is no choice of 3 puncture sphere which will generate all the full moduli space. It just doesn't fit. But each S and theta has to run exactly between 0 and infinity, right? S has to run between 0 and infinity and... Yes, exactly. Yes, it will not cover the moduli space. Yeah. I mean, if you allow the S and theta to be running independently, right, for each showing, then you can cover the moduli space. You just let it run till you fill the moduli space, right? But as long as you are, demanding that each S and theta will run over a fixed range, right, then you cannot do it with 3 punctured spheres. Yeah, I think if you want to count Teichmuller space, you may be able to do that, right? Even that I am not completely sure, but you may be able to do that. Yeah.
But even 4 punctured sphere, I don't think.
Yeah, even 4 punctured sphere, even Teichmuller space, it will be hard to cover. No, you can do it, but if you want each S and theta to run from 0 to infinity.
I agree that I don't know about the covering moduli space exactly 125
Yeah, that's true. But the point is that you want to make sure that as S goes from 0 to infinity, you cover the Teichmuller space only once. See, if you are willing to cover Teichmuller space multiple times, then you can do it. Right? It should be that over this range you should cover it only once, right? So that is hard with 3 punctured sphere. Okay, so what we will do is that we will denote by R bar GMN the section segment and once R bar GMN is given, okay, then in principle everything else is also given because you just sew them together. Okay. However, this has very tight constraints. Okay. Not every choice of R bar GMN will do. Okay. This is constrained so that we do not leave a gap. Okay, this is the condition. I mean, this is precisely the reason why just having 3 punctured sphere is not good enough. Okay, you will leave a gap. Okay, or you will cover too much. So let me give some example. So suppose we begin with R bar, say 0, 3, 0. Okay, so this is genus 0, 3 NS punctures, no Raman punctures. Okay, so this is in terms of Feynman diagram, we are given some is genus 0 contribution to this vortex.
And where you need G for all G?
Yes, you need G for all G, which is a little surprising because normally you think of the elementary vortex as only coming from genus 0. Right? But what it turns out that the action that will get this way is what is called a BV quantized action, right? Which in fact also knows about the fact that the measure is not modular, not gauge invariant. Okay? And so normally what happens is sometimes you may start with the gauge theory where you write down an action and then you find that the measure is not gauge invariant, right? And then you add compensating term in terms of additional counter term in the action, right? Because this comes in the BV formalism, right? All those counter terms are also included explicitly in the definition of the action. Okay, so indeed you need vertices even for non-zero G, okay? But those are necessary in order to ensure that the action together with the measure is invariant under gauge transformation.
Like a quantum effective.
Yes, well this is not quantum effective action. This is
Still do a path integral.
Yes, you will have to still do a path integral. This comes in this BV formalism, so you still have to do a full path integral over this, right? But you don't have to make any more compensation for the measure not being gauge invariant, right? This ensures that you automatically get gauge invariant answer without having to worry about the gauge invariance of the measure. Okay, that is already taken into account these corrections for non-zero G. Okay, so starting with this, then we can draw a ST and U channel diagram. So let's say 1, 2, 3, 4. Then, sorry, 1, 2, 3, 4, and 1, 2, 3, 4. You can write down the usual kind of action, but only at a classical level, right? And then when you do quantization, you will find that you have to automatically add these additional terms because the path integral method is not gauge invariant. So certainly there is a way, there is a notion of writing down the classical action, which is just that you restrict to genus 0. Right? But then you will discover that you are running into problems because this quantum theory, you destroy gauge invariance unless you add these counter terms, right? Which you can identify as the measure not being gauge invariant.
Why is the genus related to this reaction?
Yeah, it just so happens that somehow the action that you get from this construction, right, automatically takes into account possible non-gauge invariance of the measure. Okay? Because the action that you are getting is designed to reproduce the string amplitudes, right, which you know are modular invariant and has no gauge anomaly, right?
It has all these ghosts and ghosts of ghosts.
Exactly. So it automatically will have everything.
Okay, so but why does that involve higher genus?
Because typically in the BV master action, right, what you call the quantum master action, you have to add higher genus corrections, higher loop corrections. It has an expansion in powers of h bar.
Okay, so the quantum master equation.
Yeah, so this is quantum master action. What we get from this construction is what is called quantum master action.
Okay, so the h bar in this e to the power s over h bar.
Yes, that is GS. That will be the G string, right, which is the genus expansion parameter.
Okay, and since you need in general infinite powers of h bar.
Yes.
You're saying those are those.
Those are those terms, exactly. The vertices that you need for higher genus are those, right, which are like powers of h bar.
But is there a sense in which the higher and higher genus guys involve more and more ghosts of ghosts? And the ghost number also?
No, not necessarily.
Not necessarily.
No, even for low ghost numbers, you get couplings at higher genus. So in general, this is not the case, right, in BB formalism.
And M and N also grow with.
Yes, M and N. This you'll have all M and N. I mean, yeah, non-polynomial action. Elementary couplings.
If you wanted to compute the elementary couplings, you have to go back to the Polyakov formulation.
Yes, you have to go back to the Polyakov formulation, but I'll describe in what way this is better than the Polyakov formulation, because Polyakov formulation had the problem with the infrared divergences, right? We'll see that the elementary vertices have no infrared divergence. Right? That's the advantage of these elementary vertices. Okay, and that I'll discuss in a few minutes. Okay, so these are the Feynman diagrams. Suppose you have gotten R bar 0, 0, right, which of course has no infrared divergence. This is a 3-puncture sphere, no modular integral at all. Okay. Then by joining these vertices, you can construct this. So these give you section segments. Okay. So if you now consider P tilde 0, 4, 0, right, what will happen is that the S channel diagram will give some segment, T channel diagram will give something, U channel diagram will give something. And then your total section should be a continuous segment. Okay? Total section should be a continuous section. So now you fill the gaps. Okay? There is a lot of ambiguity in how you fill the gaps, right? You can go up and down, you can do many things. Okay? And you declare these, the union of all of these, to be R bar 0, 4, 0. That's the way you choose your R bar 0, 4, 0. Okay, because after all, the total 4-point amplitude is these 3 plus this. Okay, this is something that I have not specified yet. These are already specified by the 3-puncture sphere. Okay. So now you associate with this a new region of P tilde 0, 4, 0, which is R bar 0, 4, 0, and those are these dotted regions that you need to fill.
Does R bar 0, 4, 0 contain the boundary?
No, it doesn't. It doesn't. So maybe this diagram is not correct, right? Maybe I should, well, this is a one-dimensional diagram I have drawn, right? So that's what I was going to discuss next, that the boundaries, see what are the boundaries of the model space, right? Those are the ones where two punctures come close together, right? Any two punctures. Those all correspond to the s goes to infinity limit of this diagram or this diagram or this diagram. Okay? If you take the Swinger parameter for this, okay, and take it to infinity, okay, this will correspond to a degeneration of this kind. Okay, 1, 2, 3, 4. Okay, to take this propagator and take the corresponding Swinger parameter to infinity, that will correspond to Riemann surfaces of this kind. Okay. Here, if you take this propagator and take its Swinger parameter to infinity, that will correspond to a degeneration where 1 and 3 are on the first sphere, 2 and 4 on the second sphere. And similarly, this one will be where 1 and 4 are on the first sphere, 2 and 3 will be on the second sphere. Okay. So all the degeneration limits are already covered by these diagrams. Okay. So this R bar 040, okay, that you need to fill these gaps, okay, they never contain any degenerate Riemann surface. Okay. And because of this, our computation of R bar 040, right, has no ambiguities or no, well, it has ambiguities in the sense that of course you have to choose these sections arbitrarily, but it has no divergences, okay, of the kind that we encountered in Polyakov amplitude. Okay, that's the main difference between computing R bar 040, okay, and in general R bar GMN, okay, as opposed to the usual string scattering amplitudes. Yes. You don't know ahead of time. You have to start with R bar 030, right? Here, of course, there is a lot of ambiguity, how you choose the PCO location and what local coordinates you choose. Once you have made that choice, you can compute each of these diagrams, right? Take s and theta from 0 to infinity and theta from 0 to 2 pi, and see which part of the region you cover, right? Whatever is not covered is by definition is R bar 040, right? You join the boundaries, okay, with some section, right, which again, I mean, how the vertical direction, the boundaries are fixed, right, but the actual section segment is not fixed. There's an ambiguity. But you declare, you choose some section segment, you declare that to be R bar 040. Okay. Yeah, even in the 4-point amplitude, the infrared divergences occur, right? Yeah. Yes, for bosonic string. Yes. Exactly. This part, these solid ones. Yes. Exactly. In tree level, it is possible to do in practice, right? You can get it by Strebel quadratic differential, right? At loop level, you have to do it maybe numerically, right? You can put it on a computer, see which region is covered, okay, and then you cover the rest by what you call R bar GMN. Okay, but in principle, the main point is that this definition of R bar GMN. See, at the end, we need very little information about what these R bars are. Okay? Because, as I said, different choices of R bars are related by field definition. So the physical quantities shouldn't depend on how you have chosen your R bar. Okay? But just to be able to carry out the usual field theory manipulations, you need an action which is free from any divergences. Right? Because you cannot deal with divergent quantities from the beginning, right? Because then you, I mean, once you have an infinity, then you don't know what you are doing, right? So this lets you organize things in a way so that you have quantities in which there are no divergences. Right? Then you know where the possible divergences could come from, and those will be the usual infrared divergences of a field theory, but the Swinger parameter goes to infinity. And then those you deal with by using the standard field theory techniques. And so that's the basic philosophy behind this using string field theory. Yes. Exactly. That's right.
That is also a non-trivial.
At the tree level, as I said, it can be done, right? Because this trivial quadratic differentials lets to do that. I mean, how to translate between the different moduli parameters, right? But whatever the translation may be, right, that may depend. In fact, you can try to simplify your life. At least at the tree level, you can try to simplify your life by using this choice of local coordinates as related to the regular sphere coordinates by an SL2C transformation. Right? Once, if there's SL to C transformation, then it's very easy to translate back and forth between the usual modular parameters and these S and T parameters, right? Because they are just gluing by SL to C transformation. Okay. If you have more general local coordinate choice, right, then the analysis is more difficult, right? But in principle, it can be done. Yes.
When we do this in field theory,
Yes.
when we have a field theory where we need formalism and when we're fixing counter terms, so the kind of counter terms that are allowed, we already know it beforehand by solving the master equation.
Yes.
Right? You know, like the master equation gives, and then we can fix various terms. You know, in a particular way of doing,
yeah,
in a particular scheme or something, we can fix it.
Yeah.
So here, do we know already by, is there an analog where we can use some master equation to say which form is R bar 040?
Oh, any form of R bar 040, as long as it fills the region, will be a solution to the master equation. Right? So what you can show is that the solving the master equation, okay, is precisely equivalent to R bars filling the regions.
Is there a way to use that fact to explicitly do this?
Well, you can do that, except that again it will not fix it uniquely, right? The kind of ambiguity that you encountered in trying to cover the region of the moduli space is exactly the same ambiguity that you will get by writing down a BV master equation and trying to solve it, right? Because mathematically they are identical problems.
Yes. So
right?
You do get ambiguities in the counter term.
Exactly, that's right.
It's only by some scheme or something.
Exactly. So those ambiguities are the ambiguities that you are encountering here, right? So you can reformulate this one, right? Here you are thinking of this as producing the off-shell amplitude, right? Instead of we don't even know that it corresponds to the master action, right? But you could start from the other end, right? You could say that you write down the general BV master equation, and then you can solve them to discover this, and mathematically you find that it's exactly the same problem.
So I can do a H-bar perturbation theory of the BV master equation.
Exactly. So if you start from the classical string field theory action and then you try to find the counter terms by using H-bar perturbation theory, you will encounter exactly the same equations that determine these regions. Right? Because see, in a sense, you can see that this is related to gauge invariance, because gauge invariance in the worldsheet theory, right, involves integral of total derivatives. Right? Typically, when you are inside a pure gauge state, you get integrals over total derivatives, right? And in order to show that they vanish, you have to better make sure that it's a continuous section, right? If these two ends do not match up, then you will be left with boundary terms over here, right? So it's precisely the requirement that those boundary terms are absent, right, is the requirement of BV master equation, right? And that's being seen here as these dotted lines joining the solid lines correctly, right? That this is a continuous section.
I can rephrase maybe the first of his question slightly differently. I think he was maybe trying to ask whether there's a constructive way to here, in a sense, the R bar GMN are described recursively and in a sense
yes,
complementary to the it's a complementary to what you construct from the lower genus answers. But I think maybe he was trying to ask whether this helps you to constructively just get the integrals in. Finally, you will be writing the Polyakov integrals over this R bar GMN.
Yes.
What the value of those integrals are, whether that is.
I see. That I think is very complicated typically, right? If you have, general external off-shell states to write down the value of those integrals, I think the simplest way to represent them is as integrals over the moduli space, right? I don't know of any way to actually write down the values, right? Those are not likely to be very simple. If you take a generic vertex operator, right, completely off-shell vertex operators, probably it's very hard to find expressions. Although in principle, you could ask that you are given the tree level action, right? Suppose you didn't know anything about worldsheet theory, right? You are given a tree-level action, and can you algebraically solve those equations, right? And you may do hard work and algebraically solve those equations. Then you have to also do expansion in the in the field levels, right? Here you are getting you are not worried about the field levels, right? You are getting everything at one go, right? You will get an expansion in the field levels, and you will probably get the same conditions because you are solving the same equations. Right? But I think that will be a much harder thing to do, right? Although in principle it is certainly possible to do it constructively.
So in the BB formalism, you have e to the power s over h bar being closed, is in some sense the BB master.
Yes.
So should I think of this particular form that you are integrating over?
Yes.
As the e to the power s over h bar? Is that
No. I'll write down the action, then the S will become clear. See, right now this is still first quantized formulation, right? I'm just building up the off-cell amplitudes, but all in the first quantized formulation, right? I'm just drawing insight from Feynman diagrams analysis, but I have not said about what the second quantized action is and what the propagator is and so on, right? I'll write down the action, right, by the end of the day, and that will be the BV master action.
okay? And so that's next way I can identify the BV Laplacian and so on.
Yes, exactly.
And that exactly gives you this closed.
Exactly. So that will satisfy this master equation, the SS plus delta S there. This is the quantum correction, right? H bar delta S equal to 0. Right? So the content of this, right, is the fact that this arch bar GMNs fill it, right? Although of course right now you don't see it at all because you have not even seen the action. Yes. No. Well, R bar doesn't depend on the vertex operator. See, R bar 030 is just a purely geometric object. It's some point in P tilde 030, right? It's a zero-dimensional space. It doesn't depend on the vertex operator. Yes. So I'll describe what this propagator means. Right? So I have not described that yet. So this plumbing fixture, right, will be reinterpreted as a sum of all states in the intermediate state. Okay, I have not shown yet why this is a propagator, right? I have just said that the analog of joining two 3-point vertex by something is the plumbing fixture, but I have not said why, right? This is just an intuition so far, but I'll write down precisely why this is like summing over propagator. Right? And that will become clear once I again write down the field theory. Is this okay? It will correspond to some interior point in the solid line. So probably this diagram is not very illustrative, right? The boundaries of the moduli space are sitting somewhere in the interior of the solid line. Well, that can be changed, right? If you change, for example, the definition of R bar 030. R bar 030, for example, contains information about the picture changing operators where you are located, right? Also the endpoints, also the local coordinates at the 3 punctures. By changing those, you can extend these and you can string the dotted lines, right? Or in fact, what is more useful way of viewing this is that you basically extend the dotted lines, right? You can ensure that the S, T and U channel diagrams cover only a very small region around the boundary. Okay, so the boundary is still cut off. Okay, and the dotted lines, the elementary vertex basically gives most of the region of the moduli space. Okay, so these boundaries can be moved around by making different choices of R bar 030. In that sense, they don't have any, absolute significance. Okay, so now let me try to convert this into Feynman rules. So first the vortices, these are easier. Okay. So what is a vortex? A vortex is typically some endpoint function, okay, A1, A2, these are the external states up to n. Okay. I'll use a symbol, okay, the double bracket of A1 to n. Okay. And by definition, this is integral over R bar Gmn sum over genus. This is the string coupling. Where m and n depends on how many are Nebel-Schwarz and how many are Ramond in this, right? So n is m plus n. Okay, because this Feynman diagram by definition, okay, is given by this, right? And that's what the vortex represents. Okay, and I should always add that whenever I am talking about Feynman diagram, okay, I am not counting the external propagators, right? It's really the vortex. That's what the Polyakov amplitudes compute. Now, the harder part, the propagator. So let me draw this diagram again. So suppose we have two Riemann surfaces with some functions. This is the, we have sorted them. So this is our mod W2 equal to 1. This is mod W1 equal to 1. Okay. And we have this identification W1, W2 equal to e to the minus s plus I theta. So what we are going to do, okay, to see what this plumbing fixture gives, okay, is you insert a complete set of states on this circle, mod W1 equal to 1 circle and mod W2 equal to 1 circle, okay, by writing this as insert sum over R chi R C, okay, this we insert here, okay, and on this I insert sum over R, sorry, sum over S, okay, where what is chi R? This these are the basis states in the full Hilbert space. In full Hilbert space, satisfying the orthonormality condition that chi RC, chi S is delta RS. Okay, that's the definition of chi R.
Full means not that H.
No, not that HT. It's the complete Hilbert space, because in a conformal field theory, I mean, once you have a Riemann surface, right? I mean, nobody tells you that what can propagate there. It has to be determined by dynamics, right? So in principle, every state can propagate. So you introduce a basis state in the full Hilbert space, right? Eventually, our goal will be to show that only the states in HT propagate, right? But at this stage, you have the full Hilbert space built in here. So the idea is that when you carry out the path integral over this Riemann surface, right, that's what the correlation function is supposed to be. Okay, you carry out the path integral over this part first, carry out the path integral over this part first, Okay, those are easy because carrying out path integral over this part means that you are essentially inserting this chi r on the Riemann surface at this puncture. Okay. Carrying out path integral over this means that you are inserting this chi sc, right? Because this is what's going this way. You are inserting chi sc on this Riemann surface, and in between here you have a matrix element. Yes, small Hilbert space because you are not using the Xi0 mode, but otherwise you don't put any restriction on B0 minus annihilation or L0 minus annihilation or anything. Because those are the restrictions we put by hand, but there is no reason why you should have those restrictions built in. Okay, so on the propagator, right, let's see what is inserted here. On this, right, what will be the contribution from this? So first of all, you have the integrals over the s and theta, because plumbing fixture requires that we integrate over this. Then you have sum over, we have chi r. Okay, let me write this down and then I'll explain various factors. G, let me define first. So G is identity on NS sector and chi naught on R sector. Okay. So this you can understand easily because you had introduced that integral over chi of W, that's your chi 0. So chi 0 is integral dW by chi of W. Okay, in Ramon sector, gluing, we had to insert an extra chi 0, so that's what this G stands for. Now, what is B0 plus? Where did the B0 plus come from? Okay. So, you are integrating in the s and theta direction, so the this omega, right, has to be contracted with the tangent vectors del s and del theta, right, because you are doing the integral ds d theta. If you want to integrate omega along that s and theta direction, you have to contract it to tangent vectors del s and del theta. Okay. Contraction of the tangent vector del s, if you follow the rules that I gave, okay, gives you B0 plus. Okay. And the contraction with del theta gives you B0 minus. Is this clear? You just follow the rules that you had the integral over B, if you remember, right? Integral over B field that you have to insert in the correlation function in order to carry out this contraction, and if you do this integral explicitly, you will find that it's exactly the operators B0 plus and B0 minus. These ones are generating conformal transformation. Okay. Remember that we can write this as W2 equal to e to the minus s plus I theta over W1. Okay. So there is a scaling by e to the minus s plus I theta, so that's what this is doing. Okay, it's scaling z by e to the minus s plus I theta and z bar by e to the minus s minus I theta. That's what the origin of these factors. Okay. And finally, the fact that you have a 1 over W1, okay, is reflected in the fact that one of the states is BPC conjugated. Okay, it's chi r c rather than chi r the kate vector. So let me summarize. Okay, so what this is saying is that this amplitude, okay, which you get by showing, okay, is given by a product of three factors. One is a correlation function on this Riemann surface, where these are the usual external vertex operators, and here instead of having this disk, you remove this disk, you fill the Riemann surface, and you insert at W1 equal to 0 the vertex operator that is appearing here, chi r. Similarly, for this Riemann surface, okay, you close this disk, you forget about the fact that you have ever done a plumbing fixture, it's as if it's the original Riemann surface, and at W2 equal to 0, you insert the vertex operator chi sc. and then you sum over R and S multiplied by this factor over here. Okay, so this is playing the role of the propagator. Okay, and here you see the internal states explicitly appearing. Okay, so this is the propagator with index R and S. Okay, R is the state that is appearing on the left hand side, S is the state that is appearing on the right hand side. So if I have to draw the figure, so this is some Feynman diagrams. Here is R, here is S. Okay, and this is the delta S propagator.
L0 bar.
Yes.
They come from where in the
This is a scaling, because W2 is 1 over W1 times the scaling, right? So the scaling is being performed by this explicitly e to the minus S plus I theta L0 and e to the minus S minus I theta L0 bar.
L0 plus.
Yes, L0. So S multiplies L0 plus and theta multiplies L0 minus. See, it's S plus I Z. So W2 is e to the minus S plus I theta by W1, and W2 bar will be e to the minus S minus I theta by W1 bar. Right? So you can think of S being associated with L0 plus L0 bar and theta being associated with L0 minus L0 bar.
Just doing this coordinate transformation, it goes from this fashion.
Exactly, that's right. Okay, because you have one state here and one state here, but you are propagating here, right? The integration over this cylinder. Okay. See, when S is equal to 0, then this is collapsed, right? So then the two are the same. So then you don't need this e to the minus S. Okay, it just becomes 1, right? But for non-zero S, right, you are propagating from this end to this end. You are scaling by a factor of e to the minus S, and that's what that one is doing. Okay. Now you can do the integral over S and theta. So what you get is chi RC B0 plus B0 minus 1 over L0 plus L0 bar delta L0 bar pi S. Oh, G, yes. There is a G here. Thank you. Okay, in fact, this G is important because in the NS sector, it's 1 over L0 plus L0 bar, right? And if you recall the form of L0 plus L0 bar, this is basically k square by 2 plus a constant, right? On the this is the momentum contribution to L0 plus L0 bar plus a constant. So you can see that this is like the usual propagator factor, 1 over k square plus m square. Right? And this G is needed because in the Raman sector, which contains the fermions, you know that there is a numerator also, right? This is P slash plus m over P square plus m square, right? And this G provides the P slash plus m factor. Okay, so that's the way you get the propagator from this formalism.
Changing operator becomes a P slash plus.
Yes, that's right. That becomes a P slash plus m. In the acting on a massless states, that gives a P slash. Right?
So, changing operator with the B0s becomes the P slash m or becomes the B0s?
Well, the B0s, we'll see the role of the B0s, right? When you take the actual matrix element, right, it just gives P slash plus m over P square plus m square. B0s are needed to basically soak up certain modes. When you write down the action, probably it will become clearer. That G gives you.
Well, the G gives you.
Well, it's not completely obvious, and it's not true for on every state, right? It's true only from the on a subset of states which are normally called the physical states or analog of physical states, because G has this e to the minus phi tf, right? There is a part of G which has e to the phi tf, Okay, this TF contains psi mu del x mu. Right, so this del x mu brings down a factor of k mu, and the psi mu is like a gamma matrix. Right? That's how you get the P/slash factor. But that of course requires taking the matrix element between specific states, right? If you have a complicated host excitation on this side and this side, then this operator is quite different. Okay, are there any questions?
Eventually, you will probably be arguing that higher and highest come only from the small.
That's right, yeah. Yeah. In fact, I can argue it at this stage, but I can also go back to the, write down an action first, and then I'll argue that the string field belongs to the small Hilbert space. But one can also check at this stage itself.
Yeah, even just the path integral of the, if your original vertex operator insertions are in the HT, then the state chi-r can only be in HT.
Exactly.
When you do the path integrals.
Yeah, exactly. Yeah, but from this also you can see that this B0 minus, for example, right, means that this chi-r C and chi-s but must both contain a C0 minus. Okay, so they are conjugates which are being inserted on the Riemann surface. Okay? They should be annotated by B0 minus.
That's what was confusing.
Yeah, so these will have C0 minus because these are the conjugates of the ones that are being inserted on the Riemann surface. Okay? But I think I can do it at this stage, but it's easier to do it at the level of the action, right? Because there it will become clear what condition it will satisfy. So now, question is, what is the action? Okay, we have got the vortex, we have got the propagator, right? But now we have to see if there is an action which actually gives rise to this vortex and propagator. Okay, but before I give the action, I have to say how to represent the string field in a convenient form. Okay. So we have introduced this basis states chi-r. Okay. So any state in the Hilbert space, okay, not in the B0 minus annihilated Hilbert space, any state in the Hilbert space can be rewritten, can be expanded as psi r, phi r. Sorry, psi r, chi r. Let's call it chi r. This is a complete set of basis states. Okay. Now, these, well, I can also write it in a slightly different way. So this sum over R index, right, will contain some discrete levels, some continuous levels. So I can write this as sum over n, which is the discrete level, and then integral over the continuous index, which is the momentum index. Okay, assuming that there are d non-compact dimensions. Okay, and I can write this as psi r of k. Let's call it chi tilde r of k, or some other name. Phi r of k. Okay. In other words, all I'm saying is that the basis states, the n, that the basis states, instead of being labeled by just one index, okay, should really be thought of as being labeled by a discrete index n, okay, which is like oscillator levels or various other discrete levels, and the continuous level k. Okay. And what we will do is that we will take the psi and k's, these are the fields of the problem of string field theory, okay, but fields in momentum space. Okay, the action that I will be writing will be in the momentum space. Yes.
This full Hilbert space contains incorporate GSO projection.
Okay, let's take it incorporates GSO projection. Okay, if it doesn't, it will automatically have the GSO projection built in, right, as we will see.
Do the sum over spin circle.
Yes, that's right. Okay, so the point is at this stage, I am allowing this to be arbitrary basis states in the full Hilbert space, but of course, eventually you want to show that the contribution comes only from a subspace and you can restrict psi to be that subspace, right? That's what we will do. But at this stage, okay, let's take GSO even states, right? Because that's a parity, right? So you will never mix the GSO even states with GSO odd states. Okay, so you can restrict to GSO even states, but no further restriction. Okay, so then the claim is that if we think of the fields, string field this way, okay, these are the fields of the string field theory, okay, then the action that reproduces this propagator and the vertex that I wrote down formally, and we'll explain why formally. Let me put a 1 over gs square, okay, because this is what is the standard convention. So this one is the usual vertex, because our vertex with n external states was a1, a2 up to n with this curly bracket, right? So if you take psi to the n, what does it mean? This basically means that the curly bracket of n psi is inserted. Okay. And the 1 over n factorial is the usual 1 over n factorial that multiplies an n-point vertex, so that when you compute this diagram, okay, when you compute this diagram from this vertex, okay, you will get exactly a1, a2 up to n. Okay, so the vertex is easy to write down. Okay. It's not hard to see that this term, oh, there's a delta L0 minus, okay, let's put delta L0 minus here, that this term, okay, would be the inverse of this operator over here, okay, because propagator should be the inverse of the kinetic term. Okay, because the C0 minus, C0 plus, okay, basically when you take the anti-commutator, you just get identity here. Okay, and the 1 over L0 plus L0 bar is cancelled by L0 plus, G inverse will be cancelled by G. Okay, so this would be a perfectly good action for this, except that this doesn't exist. This G inverse doesn't exist. So we are going to return to this problem in a few minutes, but before that, let's just try to understand what space does psi take value in. Okay. So we had introduced this basis states chi r, right? Okay. But now, this chi r, the whole set of chi r, I will now divide up into 4 different subsets. Let me call this xi a. This xi a satisfies the condition that b0 plus on xi a is 0 and b0 minus on xi a is 0. Then you have c0 minus on xi a, C0 plus on xi a, and C0 minus C0 plus on xi a. Okay, so let's suppose that you have divided out the set of basis states in this way. Okay, there is a basis set of basis states which are generated by B0 plus minus, then you have C0 minus acting on this, C0 plus acting on this, and C0 minus C0 plus acting on this. Okay. And the BPZ inner product, okay, basically pairs this xi a with C0 minus C0 plus xi a, okay, and this one with this one. Okay, because you need the C0 modes to be soaked up. Okay, so that's the way the pairing goes. This one is conjugate to this one, okay, and these two are conjugate to each other. Now let's look at this matrix element over here. Okay, let's forget about the G for the time being, because G inverse doesn't exist anywhere, so let's forget about it for now, okay, and we'll later include this. So you can see that if psi belongs to either this one, or this one, the result is 0 for the matrix element. Right? Because the C0 plus, either you will get a C0 plus square, or you will get a C0 minus square, or you will get a C0 minus square, C0 plus square, all of those are 0. Okay. So the only component of psi that contributes, okay, is the one that has that's here. Is this point clear? Okay. So psi can be restricted to satisfy B0 minus psi equal to 0 and B0 plus psi equal to 0. Okay. This in fact you can also see from here. Okay. If you use the same criteria, here you have a B0 plus B0 minus sitting here. Okay. So the only way this matrix element can be non-zero is both chi s has to belong to this and that chi rc has to belong to this. Okay, because you have one extra B0 plus and B0 minus, so you have to have, ultimately you need a C0 plus and C0 minus to get a non-zero matrix element. So you need a C0 plus C0 minus from here, which will compensate for the B0 plus B0 minus, and another C0 plus C0 minus for here, which will eventually produce a non-zero matrix element. Okay, so if chi s belongs to this, then its conjugate, which is actually inserted in on the Riemann surface, must belong to this, right? Because these are paired, and similarly for this. Okay. So this tells us that the string field, which is actually inserted on the correlation function, has to satisfy these two conditions. And then you can also work out the picture number, okay, from this, that once the picture numbers of all the external states are fixed, okay, which is to be in h hat t, and these are in h hat t, you can easily check that the picture number that is to be inserted here should be either -1 or -half, depending on whether it's ns or r, and similarly the picture number that has to be inserted here is either -1 or -half, that's ns or r. Okay, so you can really say that the string field psi belongs to h hat t, okay, with the further condition that B0 plus psi is equal to 0. Okay, so this is the action you have found. So you take a string field, okay, by which I mean that you take an expansion of this kind, but the basis states that you allowed in this expansion, okay, are the ones which are in h hat t, and furthermore they are annotated by B0 plus. Yes. It will not have gauge invariance. Okay, this is a gauge fixed version, but when you write down the gauge unfixed version, you will find that if you don't include the higher order vertices, it will not have gauge invariance.
If I just define tree amplitude to the cubic vertex, it would be like integrating on some subset of moduli.
Exactly. That's right. So if you, that means your section will have gaps, right? So when you now try to check for gauge invariance, so that if a pure gauge state decouples, you have integral over total derivative in the moduli space, right? And it will leave out the boundary terms at those gaps. if you fix the gauge, right, then yes, these amplitudes are unitary by construction, well, except that they have negative non-states. Okay, and normally what we have to show is that those negative non-states actually decouple by cancelling against other things. Right? That will fail for this action. Right? Because you are having a covariantly gauge fixed action, where of course because you have gauge fixed you can throw away certain terms. Right? But what will fail is that you will not have the decoupling of those unphysical states which you want to decouple. So you need the gauge invariance. Even though this is a gauge fixed action, without having the gauge invariance, you cannot show unitarity. Yes, yes. So that is the fact that the G inverse doesn't exist. Okay, so this is only a formal, I wrote down this G inverse, but it doesn't exist. Okay, so I'll now say how to repair it.
They had some kind of doubling.
Yes, so that's what I'm going to discuss now. Okay, so this action is actually fake. I mean, I wrote down this action, but it's not correct because there is no G inverse. Okay, so we needed the G inverse because the propagator has a G sitting here, right? So I'll now show how you can get a G in the propagator without writing a G inverse in the kinetic term.
Why is there no G?
Because there are states in the Hilbert space which are not G on something. So when you apply G inverse on those, right, it's an ill-defined object. So G inverse in fact is well defined on the cohomology. If you look at physical states, right, the BRST cohomology, then G inverse exists on the BRST cohomology, right? Given any state on the BRST cohomology, there is another state, G acting on which gives you the state in the BRST cohomology in the other picture, right? But because this is off-shell string field theory, here you are not demanding that a psi is in the BRST cohomology, right? So you have to really define G inverse on the full H hat T and not only on the cohomology, right? And that's the problem, that you cannot write an off-shell action with a G inverse sitting around here. And this you can trace back to the fact that a type 2 supergravity doesn't have an action. Or it's the other way. The fact that the type 2 supergravity doesn't have an action, you can trace it to the non-existence of G inverse.
So if it was just a chiral fermion,
Yes.
then the G would have, apart from a P slash, it would also have a projection.
That's right.
Chiral projection, 1 plus gamma.
Yeah.
So that is of course not invertible because of projection
Yeah.
in the whole Dirac space. Is that what is happening here?
Roughly, that's what is happening here, right? But it becomes more visible in the type 2b, where you have this 4-form field, right, which has a self-duality constant on the 5-form field strength. And that you know that even if you forget about string field theory, just as a normal field theory, you cannot write down an action for that, right? And that's precisely because this projection operator is not invertible, that you cannot write things in terms of an independent set of variables.
Yes, so so if you write a propagator for the self-dual,
Yeah.
so you have a 1 plus star.
Exactly, yeah.
That kind of a projection.
Exactly. So that doesn't have an inverse, right? That's why there's a kinetic term. That the propagator for the self-dual field, which is the 1 plus star, it doesn't have an inverse, right? Whereas for chiral fermions, at least we know that there is an action in principle, right? Which you can write down. Yes, this is roughly a problem for chiral theories, exactly.
Like the type 2A has.
Well, type 2A, the point is, it doesn't, actually, as a supergravity, it doesn't have this problem. But because the construction is very similar, right, at the level of the string field theory, you have this obstruction even for type 2A string theory, right? But it could be that there is some other way to formulate type 2A string theory, which doesn't encounter this problem. But at least this is uniformly valid for heterotic and type 2, right? And that's why once there is an obstruction, it extends to all of them.
So there is T duality.
Yeah, they are two dual to each other, but also the type 2 and type 2 we differ only in the GSO projection rules, right?
Yes.
And here the GSO projection is not playing a very important role, except that all states have been taken to be GSO even, right? But otherwise it has not played a crucial role in what you have been doing, right? We are doing really at the level of the worldsheet theory. Yes. Any question or? Okay. So the way one gets around this is that you introduce a new field psi tilde, which is in H tilde t. Still B0 plus psi tilde equal to 0. Okay. And write an action which is minus half 1 over Ts square. Okay. So the important point here is notice that the interaction term involves only psi. Okay, psi tilde has appeared only in the kinetic term. Okay. So how does this help? So to see how this helps, we can look at the kinetic operator in the matrix form. Yeah. Yeah, because you have taken, I have taken them to be H tilde t and H hat t, that's automatic, right? So you don't have to write the delta L0 explicitly. Okay. So the kinetic operator is basically C0 minus C0 plus L0 plus, okay, and then as a matrix form minus G 1 1 0. Okay. So to take the inverse, okay, which will be the propagator, you get B0 plus B0 minus L0 plus inverse. Again, delta L0 minus I am not writing because you are already in the H tilde t and H hat t space. Okay. And the inverse of this matrix is 0 1 1 G. Okay. So we see that the psi propagator, right, which is psi is this element. Okay, the psi propagator is B0 plus B0 minus L0 plus inverse G, and that's exactly what we want. Okay. And the psi propagator is the only one that is relevant because in all interactions, because the interaction vertex contains psi to the n, in all interactions what propagator appears here is the psi propagator. Okay. So when you look at the unitarity relation, okay, the what appears as physical states is the psi state. Okay. Psi tilde basically remains a free field, okay, which you can also see from the fact that it appears only in the quadratic and the linear term. Okay. So this theory then has the usual interacting string theory, which has the right amplitude, okay, and it has some extra set of fields which are completely free, and hence they are not observable. Okay, so as far as physical observables are concerned, this theory has exactly the same physical observables as a normal string theory.
The fact that you're not allowing psi tilde to be there in the
Interaction term.
Suppose there were in type 2T there was some term that looked like f by star f square. I mean,
Yeah, the point is there shouldn't be any interaction term in type 2B theory which couples to the anti-self-dual part of f. Right? That's the condition, because that will make the theory inconsistent. Right? And that's what is the is what this is. Okay. So this then is the field theory which reproduces all the amplitudes of type 2 string theory, okay, at least formally, okay, including the divergences. But in this, from this field theory, okay, divergences are all coming in the infinite Schrödinger parameter limit. So they are the standard infrared divergences. Okay. And because they are the standard infrared divergences, we can use standard field theory tricks to address those divergences. Right? That's the main advantage of this, okay, that the interaction vertices are completely finite. Okay. These, even though they are given as integrals, as Polyakov integrals, They only are given as integrals over part of the moduli space, which has no degenerate Riemann surface. Okay? All divergences are made manifest explicitly.
I mean, normally in theory, if you had mixing terms like this, you first diagonalize the quadratic term and then write the action in terms of the diagonal modes, and the vertices you write in terms of the combination. But you're not doing that here.
Yeah, I'm not doing that here because of the fact that again G is not invertible, right? See, you can see if G was identity, right? Maybe it will make it easier to see what happens if G was identity. Okay? If G was identity, right, then the kinetic term I could have written as minus half, okay, psi tilde minus psi square. Well, let me write psi tilde minus psi C0 minus C0 plus L0 plus psi tilde minus psi plus half psi C0 minus C0 plus L0 plus psi. Okay, so this would be the diagonalization that we are suggesting, right? And then once you have done that, then you take psi as the interacting field which has the interaction. Right? And this is completely a free field. Right? Is that because G is not identity, you cannot explicitly write it this way. Right? But the physical content, when you look at the physical content of the theory, it's that psi tilde represents a free field. Right? There is no degree of freedom in psi tilde which interacts.
So because you could do that even for G not, I mean, because you have inverted the quadratic term, so it's invertible. So
Yeah, it's invertible, but not writing G inverse.
Yeah. So you can write the eigenvalues then with positive.
But I think the eigenvalues will involve G inverse probably. When you try to write down the eigenvalues of as a linear combination of psi and psi tilde, right? I think those will probably involve. Yeah. The point is that what makes things simpler here is that the G has, even though G is not well defined on the full off-shell Hilbert space, right? G is well defined on the BRST cohomology, right? So acting on the physical state, G has well defined action. It can take you from psi to psi tilde and so on, right? So you can then say that you have two copies of each physical state, one in psi, one in psi tilde. Right? One particular linear combination is free, the other one is the usual interacting field, right? But it's hard to see how to write, diagonalize it explicitly in the off-shell formulation and write an action without using G inverse.
I mean, the reason I was originally asking was, this is the propagator for psi directly, but normally you would have written that the full propagator would have been this one plus the mixing terms. Psi could keep oscillating with psi and intermediate.
That is true. But between the initial and the final one, right, is a psi propagator. So when you write down the unit cutting relations, for example, right, you will never see the intermediate states, right? You will see the pole correspond to psi propagator. The full propagator that will ever come in, right, is a psi propagator and not, explicit.
The quantum corrected psi propagator.
But all of those will be, there will be the psi tilde anywhere, even quantum corrections.
In the internal, in between, because you can have psi and
Psi, if you make it psi tilde, doesn't interact, right?
Psi tilde doesn't have any.
Exactly.
No, not interaction. I was just thinking of like not going to dash.
But when you write this inverse, right, that's already taken into account. See, this fact that you got G, right, this is a full inverse, right, of the propagator.
But there is a mixing term.
There is a mixing term, but you never include diagrams like this, right, because this is a full psi propagator. See, this, you have already summed all of these, right, to write this G over here.
No, this is at the classical level.
But quantum level doesn't change anything because psi tilde never takes part in the interaction. See, suppose you derive the Feynman rules, right? In the Feynman rules, you calculate the psi propagator, psi tilde propagator. Okay? And in the psi tilde propagator, you will use the psi tilde as part of the if there is a vertex from which psi tilde was coming out, right? You have to use a psi tilde explicitly.
It's like this isn't similar to what you have in the Higgs case, where you have k square in the lower diagonal and n square off diagonal. You have the longitudinal mode. If you write in terms of some other gauge where you get a mixing between the longitudinal mode and
that's right, yeah.
You will get a propagator.
But once you invert it, right?
Yeah, when you invert it, you will get something with 1 over k square and then maybe 1 over m square. But it's when you resum the whole diagram that you get the shifted pole 1 over k square.
Yeah, but I think this is already the result of resummation. See, you can also see, as I said, if you take G equal to identity, then there's a confusion, right? Suppose you take G equal to identity, right?
I agree that this, then there are two modes. One is the size and one is psi tilde
minus psi. That is what has become free, right? But psi is the interacting mode, right? So the psi propagator is still given by the lower right corner. See, if there is one psi tilde ever produced, right, then you have to worry about its mixing with psi as well as with psi tilde. Right, because there is it's the psi which is interacting. Right? You just pick up the psi pole in the whole propagator. So this element, so what I'm saying is that this element, right, is what will always appear in the Feynman rule. That if you take two vertices, right, each with psi coming out, right, what you need to calculate, okay, is the 2-point function of psi. Okay, because you have two psi's at the two ends, right, and that's what this G is giving. So if you assume that G is invertible, then you could do this completion of square here, and you will get exactly the same thing, except that there will be some G inverse sitting somewhere. Right? Yeah, so you can pretend that G is invertible, right? Then you just complete the square. I think you will have a psi tilde minus G inverse psi. Here with a G here, and there will be a G inverse sitting inside, and when you invert that, you will get back G. So that's exactly what you will get from that corner over there.
Lower triangle nature to the propagator. If you keep on multiplying lower triangular matrices,
Yeah.
keep on getting only lower triangular.
It's not triangular.
Yeah. Well, it's not quite triangular, but yeah.
Then just non-zero lower triangular.
This is 0 on the diagonal. So I think you somehow are transposing and then multiplying. Yeah. Yeah, it's so if you multiply this by itself, right, then you will not get this thing. So you have to do a transposition and then keep multiplying. Or any G, right, not even identity, as long as it's invertible, you will have exactly the structure. So maybe I just say one more thing and then I finish. Okay, which is that this is a gauge fixed action. Okay, and as I had stated earlier, that the gauge invariant version of this. Okay. Is that we relax the B0 plus condition, we take psi equal to h hat t, psi tilde in h tilde t, and then the action is given by 1 over gs square Okay. So once you have the action, okay, you can completely forget about the worldsheet picture. Okay. Now, starting from this action, you just decompose into components. You think of this as a set of infinite number of fields. Okay. And you can carry out all the usual field theory manipulations with this. Okay. So for example, the removal of infrared divergences or the proof of unitarity, etc., okay, can all be based on just this action. Okay, without ever having to go back to the worldsheet picture. Okay, and you can also show that this is manifestly ultraviolet finite. Okay, that the momentum integrals all converge because the vertices have exponential suppression factors. Okay, sum over states explicitly converge because that also is suppressed by exponential convergence factors. Okay, so it's a perfectly well-defined quantum field theory. Okay, and you can carry out all the usual manipulations of quantum field theory with this action. Well, so maybe I just stop here. Yes. Well, I don't know. I presume that it will be unique, right? That there is probably no way to get around without using the usual string vertices. But my feeling is that it will be very difficult to do that directly by using unitarity, right? Because you have to make sure you have many negative norm states propagating, right? And you have to make sure they are cancelled. Okay. One way we know that they are cancelled is by using gauge invariance, so that there are hosts which cancel the propagation of negative norm states. Okay. And so in a sense, you have to ensure that there is gauge invariance, underlying gauge invariance, right? But if you want to know algorithmically whether that is possible, that suppose somebody gave you gauge fixed theory, right? Say Young-Mills theory in some Feynman gauge. Okay. Yeah, suppose somebody gave you the 3-point vortex of Young-Mills theory but didn't give the gauge invariance. Okay, gave you Young-Mills theory fixed in Feynman gauge. Okay, didn't tell you that it has gauge invariance. Okay, that's the analog of this action over here, right? Okay. Then the question is how easy it will be to work out that there should be an underlying gauge invariance. So you have to first make sure there is an underlying gauge invariance, right? And then use that gauge invariance to fix the higher point vortex, right? So as long as you accept that you have to have a gauge invariance, right? Then you are essentially going back to the completion of the BB master action, right? Gauge invariance, the analog of gauge invariance here is that this should solve the BB master equation, right? And that's what this action does. So this action, you can show that unless the RGMNs are fixed exactly in the way I said, that the gaps have to be filled, okay, this will not satisfy the BB master equation. Yeah.
One could have used something like this to start with the vertex and actually recover the root minus GR.
But I think you need gauge invariance. I mean, you always go via gauge invariance, right? That I mean, if somebody gave you gravity but fixed in Feynman gauge, right, where you didn't know about the gauge invariance, and it told you that you have to complete this to a unitary theory, right? That you have to first discover that there is an underlying gauge invariance that you can build in, right? Then forget about unitarity. First, try to build the gauge invariance in. Right, and then unitarity follows automatically. Right, I think it will be very hard to just take a Feynman gauge fixed theory of gravity without talking about gauge invariance, right, and try to establish a unitary theory.
I mean, just putting unitarity bounds on how fast the longitudinal modes, for example,
Yeah, I mean it could happen, but I don't know how easy it is to do that, even for gravity. Right? If you didn't impose the gauge invariance from the beginning, right, just using unitarity to fix the amplitude.
Right. Let's say somebody even gave us a 3-point on-shell amplitude.
Yeah.
And in principle, we could have
But 3.1 shell amplitude means somebody has already told you that the physical polarizations are transverse.
Someone has already told us.
Yeah, in that case, I think you have gauge invariance built in, because see, if somebody gives you this action, right, saying that psi satisfies B0 plus equal to 0 condition and B0 minus and all the other conditions, it has also longitudinal modes, right? So the fact that those decouple is an additional input, right, and that's probably equivalent to having giving you already the information that there is an underlying gauge invariance, right? So in some sense, I think while it is in principle possible that just by from unitarity, right, you can systematically try to build the theory and show that there must be an underlying gauge invariance, right? It becomes much simpler once you know that there is a gauge invariance. Then you first try to build in the gauge invariance, right, by which you can decouple all the longitudinal modes and then reconstruct the amplitude. I mean, what you are suggesting could be possible in the light cone gauge. Maybe if somebody gave you light cone gauge string field theory, where you only have the physical states, right? There you could ask that whether by unitarity you can try to build all the higher point functions, right? But if somebody gave you an action of this form and the 3-point function, right, then I feel that it's probably not very easy without discovering the gauge invariance first.
Other procedure for building up higher point reversals. Is there some modification to write down something that has only 3.1? For example, the special Wilson coordinates will in the end build up all Riemann surfaces using this pair and decomposition by integrating over only.
That's right, yeah.
So is there some form that we could build up some string, some version of this which had only 3.2?
Yeah, see, I think there is a general result by Sonoda and Zoibach that if you use symmetric vortex, which is what you need from a field theory, right, because the 3-point vortex should be symmetric in all 3 external legs, right? That if you use a symmetric vortex, then it's impossible to build the full moduli space, even at tree level, okay, just by using the 3-point vortex. That you will always either overcover some region or undercover some region of the moduli space.
In that, is there a tacit assumption of how you build the hierarchy in the string form? How you build the Riemann surface with higher functors using the Riemann surface with lower functors? They're going to use the plumbing fixture.
Yes, because you are assuming that a propagator is 1 over L0 plus L0 bar. Because you want the standard, see, if you want the standard propagator which has 1 over k square plus m square, right, then you need 1 over L0 plus L0 bar as the propagator, right? And that basically fixes the plumbing fixture as the way of going. Okay. Certainly, if you use other kinds of propagators, right, which doesn't have the 1 over L0 plus L0 bar, right, you can probably build a string field theory, right? But for those propagators, for example, deriving things like cutting rules are going to be very hard, right? At least you cannot use any of the field theory intuition to derive cutting rules because the poles will be in some strange places. Yeah, so that's one of the advantage of having this 1 over L0 plus L0 bar, that at least here the propagator has the standard poles, and so you have some hope that you can derive the cutting rules from there.
Is there, I mean, having this gauge invariant action, can one now try to revisit the light cone gauge and try to fix the
problems? Yeah. Meaning that is one thing I have thought about, but I have not really made any progress. That I mean, somehow rewrite the light cone gauge theory, right, with this insight. Right? See, the main problem is that in the light cone gauge you don't have the hosts, right? So you don't have the freedom of moving the picture changing operators at will, because hosts are basically fixed at some the analog of the picture changing operators are fixed at very special points, and then you have integrated out the host modes. Right? Whereas what you have here is that you have the freedom of moving the picture changing operators. Right? So somehow you have to see if you can put the picture changing operators in appropriate places where you avoid the singularities, right? And yet you are able to integrate out the host fields completely, right? And write things in terms of the this reduced number of variables.
I mean, I was thinking that if there's a completely gauge fixed version of this, in which you make sure there are no unphysical states at all.
Okay, yeah.
Then that would be the analog of the light cone gauge. So
that is true, yeah.
It is not exactly light cone gauge, We try to maximally gauge.
So basically you maximally gauge fields, but also you integrate all the auxiliary fields.
Yeah.
Because there are many auxiliary fields in this theory, right, which are not pure gauge, but which are just not dynamical. Yeah. So you have to integrate all of those so that there are no host excitations or any unphysical matter excitations, right? And that would be the analog of the light cone gauge. But at least it looks like it will be very highly complicated theory, right? Highly non-local interaction, higher order interactions with not very geometric intuition on what those are.
Is there a sketch of how you show that this obeys the BB master?
Yeah, well, that requires one identity, right? Should I write down that identity?
Depends on how much time.
No, I think that identity will take probably 3 or 4 minutes, even maybe 2 minutes.
Understanding it.
No, understand, to show how this, then you can believe that that identity will eventually show that this obeys the BB master equation, right?
This is an identity for what?
For the vortex. That the vortex obeys this double bracket vortex obeys certain identity, right? And that's the key to proving all the, in fact, not only the BB master equation, but everything else that you want to derive from here, right, can be derived just by knowing that identity.
So what is the physical statement of the identity?
And the physical statement of the identity is, well, it's easier to write down the thing than saying physical statement, so let me write it here. Yeah, it's not very long, so let me write it down. See, it's double bracket. Okay, so here phi s is the basis states in H hat t, phi r is the basis states in H tilde t, sorry, phi r c, and the orthonormativity condition that they satisfy is phi r c c naught minus phi s equal to delta r s. Okay, so this is the key identity that this vortex satisfies, that if we apply QB one at a time on each of these AIs, okay, it's given by, so this sum runs over all possible ways of dividing the A1 to N into two subsets. Okay, one goes here, one goes there, and this is just a single term over here. Okay. And the origin of this identity is not hard to understand, because this side, this is the integral over that RGMN, R bar GMN of the omega, right? And omega satisfies the identity that once have QB acting on in turn, it becomes d omega. Right? So this side is the integral of d omega, which is integral of the over the boundary of the RGMN. Right? And the boundary of RGMN is fixed because RGMN was the dotted lines, right? The boundary of RGMN is when the other channel diagrams are stopping. Okay? So you can figure out what is the contribution from the boundary by looking at the stopping point of the other channel diagrams. Okay, that's the S equal to 0 limit of various other diagrams, and that's where these things come from. Okay, this, for example, is the, if you take a vertex like this and take AC equal to 0, that's this contribution, right? Whereas this one is like, if you take a Feynman diagram like this and take the S equal to 0 here, okay. See, whenever this diagram, this S goes to 0, right, that's the end point of this diagram, right? So what now joins that, right? That's the elementary vertex, right? And that's what this equation is telling us. Okay? So once you use this equation, okay, then you can, using this equation, one can show that this action satisfies BB master equation. You have to define what are fields and what are anti-fields. Okay, but once you do that, you can show that it satisfies the BB master equation. You can derive all the word identities and everything from from that action and this identity. Okay, and then as I said, after this, you never have to go back to the worksheet. Okay, you just think of this as an ordinary field theory, infinite component field theory, with a kinetic term and the vertices given by that, and the vertex satisfying this identity. Okay, and you can derive everything, including unitarity. Also, how to, for example, shift background, right? When there is mass denormalization, how to shift mass. When there is a tadpole, how to shift background. Everything can be worked out in terms of this action and these vertices.
This identity comes up with many contexts.
Yeah.
D of something is equal to.
Exactly. Joining together, yeah.
That is the.
Yeah. I think in.
Universal or something.
I see.
Must write it.
I see. I think in Zoidberg's paper it was called the main identity, which is true, because that's the main identity which gives everything.
But it is there like in the exact RG equations of Polchinski.
That's true. Exactly. Yeah.
The same thing in
Yeah.
Kodera-Spencer theory.
Exactly. Yeah.
This identity.
Yeah.
There's a general.
Yeah. So this is essentially what goes in proving that satisfies the BB master equation.
So the type.
Yeah, so I can do that. Meaning this is in construction of superstring field theory, yes.
So presumably you had in mind some.
Yeah, meaning one can, for example, go through the proof of unitarity, right, and also how to shift fields and so on.
Maybe the next time you come, we'll.
Okay. Okay.